So we're going to continue to look at vector spaces whose elements are matrices. And I thought I should just sort of reiterate the method that I've been using. I've been doing this every single time, but let's make it explicit. So to check that a given set is a vector space, here's the steps that I've been going through. First, check to see if the 0 element is a member of the set that you're given. Next, pick 2 generic elements and give them names. So you write something like, let x and y be elements of V. And by generic here, I mean we assume no other conditions on x and y other than what's given in the definition of V, the way it's presented to you. So we just, okay, let x and y be elements of V. Then write down the property that they must have, since they're elements of V. So you say, okay, well, if x is an element of V and V consists of symmetric matrices, then x must have the property that its transpose is equal to itself, and go from there. So that's what I mean by write down the property they must have. And then you need to check that x plus y and cx, a scalar multiple of x, have this same property that you just wrote down. And then that will make V closed under addition and scalar multiplication. Okay, so let's continue to do this, and we're going to look at a couple of special subspaces. So let's let A be some fixed m by n matrix. Okay, so pick your favorite matrix. Call it A. All right. And suppose B is an element of Rm. Okay. So we can consider the linear system AX equals B, right? Okay, so question. Let's let W be all of the elements of Rn such that AX equals B. So W is the collection of all solutions to this linear system. Is W a vector space? Okay. So let's see. So let's check to see if 0 is an element of W. So is 0 in W? Well, then if 0 were to be in here, then we'd have to have the case that A times 0 is equal to B. Is this true? Well, only if B is equal to 0. So is W a vector space? Well, not if B is not equal to 0. Is it a vector space if B is equal to 0? Well, we still don't know that, so let's check. Okay, so let's take the collection of all solutions to the homogeneous equation. Okay, is this a vector space? Well, let's see. So, and you know what? Yeah, okay, we'll go with that. Okay, so let's take a couple of generic elements from V. So let U and V be elements of V. Okay, so that's my step 2. Step 3 says write down the property that they must have. So then we know that A times U is equal to 0, and A times V is equal to 0, because that's what it means to be elements of this set. Okay, step 4, check that the sum and scalar multiple have the same property. So U plus V. Is U plus V a solution for the homogeneous equation? What do I need to do? Well, this set consists of all things that, when multiplied by A, give you 0. How do you check if you're in there? Multiply by A and see if you get 0. Okay, so then the name of the game is multiply by A and see what we get. How do you manipulate this expression? What can I do with this? Well, the only sort of arithmetical maneuver that jumps out is like, I can distribute a product across a sum. Okay, is that any good? I don't know. Just do it. See if you get anywhere. All right. Are we any better off? Oh, well now actually we are, because this term I recognize I know something about. And also the same thing, this term I recognize I know something about. So I can use that information there. Say, okay, so then this is going to be 0 plus 0, where I'm using that information here and this information there. And I get 0. So if I multiply the sum by a, I get 0. So that tells me then that the sum is an element of V, because V contains everything that goes to 0 when you multiply by a. Great. Okay, so we did the sum. What about a scalar multiple? Well, again, how do I determine if the scalar multiple is in V? Well, you go back to the criterion of membership for V. You're in V precisely when a times u is equal to 0. So let's do a times u. Multiply yourself by a and see what you get. So, well, we know that scalars are slippery, so we can squeeze it out to the front. That'll be fine. And then we know that I can evaluate a times u, and by the way we chose u in the first place, we know that a times u is 0. So this boils down to 0. So apparently a times the scalar multiple is 0. That means that the scalar multiple is an element of V. So V is a vector space. And in fact, it's a special vector space. It's called the null space of A. Null space. So the null space of A is the collection of solutions to the associated homogeneous system.